So it's my pleasure to introduce and host now ROMER Talks Eren Aksoy from Sweden. Especially my pleasure because Eren and I did our PhDs under the supervision of the same supervisor in Göttingen. While I was finishing my PhD, Eren started as a PhD student with my supervisor, so it's really nice to have him here. So Eren is an associate professor, Halmstad University in Sweden. He coordinates Horizon Europe project Worldview, which focuses on robust automated driving in extreme weather conditions. He obtained his PhD in computer science from the University of Göttingen, Germany, in 2012. During his PhD studies, he invented the concept of semantic event chains, which is a really interesting framework to encode, learn, and execute human manipulation actions in the context of robot imitation learning. This framework has been used successfully in many different projects. Before starting in Sweden, he spent 3 years as a postdoctoral researcher with Tommy Masler in Karlsruhe Institute of Technology. Recently, he has been a visiting scholar, working on several problems with Volvo GTT and ZenX AB in Sweden. He serves as an associate editor with many journals, and he helps with the organization of many conferences. His research interests include scene semantics, computer vision, AI, and cognitive robotics. And today we'll listen to some of his research. Thank you.
Thank you, Sinan. I'm really happy to be here, and thanks a lot for the invitation. We stay in English, right? It's totally fine. Okay. And also sorry for having this short notice because it was kind of spontaneously decided. Again, my name is Eren Aksoy. I'm leading a SPIN lab, Semantic Perception Lab in Sweden. My background is computer vision and robotics. I have been working in slightly relevant tasks in both fields, robot manipulators as well as autonomous vehicles. So today I will do my best to entertain you in both subjects. I will first start with semantics-aware learning in robot manipulators. Then we will switch to the same concept for autonomous vehicles. It may sound a bit irrelevant in the beginning, but I will do my best to convince you that indeed we are trying to solve pretty much the same problem, perception. Either you are in the closed environment where you have a full power of controlling the lighting and objects and everything in the scene. On the other hand, when you start talking about those guys, autonomous vehicles, you pretty much try to solve the same thing, but in this case, the objects are becoming bigger, a bit more complicated maybe, but still the same problem. So if the laser works, I don't know, maybe I should just, this works, but that one was actually working. Maybe I have to switch, yeah, should be like that. No, it works now. So we will now start with semantics-aware learning in robot manipulators, the left-hand side. I will simplify the things because it's a work of my last, I will say 15 years of the research activity. So I will simplify the things. I will highlight some works here and there, and we will, I can dive into more details in case you want to see something interesting for your own research here. So let's assume that we want to make a sandwich, okay? So it's a very oversimplified scenario. For sure, we can use different types of vegetables like cheese, cucumber, salami, whatever you want to have. And we humans are super good at putting them in different orders to make sandwiches in different size, shape, and even taste, right? We're super skilled. Please pay attention that there is a huge variation here in the object and action domain. You can use any kind of vegetables. Today, you want to go with cucumber. Tomorrow, you may just forget about that. You may use carrot and so on. And it's all depending on your creativity and method of taste. So this is still a research question in science because we still don't know how we humans can recognize, learn, and even execute those different combinations, the variations in the object and action space. How are we managing this thing to reach the final concept of making a sandwich? This is $1 million question, which we don't know the answer, but in cognitive robotics, this is basically called signal-to-symbol or symbol grounding problem. So at the signal level, we have a very continuous sensory data, like your camera images, or your point clouds, or your trajectory information, whatever you have. And at the symbolic level, we are talking about the plans, primitives, like grasp, approach, cut. Okay, so those are the plans. Those are the those are the raw sensory data. And if you take a look at the literature, you may see that there is a large group working just on this continuous data, like Staffan Schall and so on. They just take a look at raw trajectory information and apply complicated reinforcement learning techniques to just imitate these works, which is working very nicely. There is no question about that, but they are skipping this symbolic representation. On the other hand, there's another group working just purely on the primitive level, symbolic information, assuming that they are already grounded, that they can put those symbolics together, complicated primitives together, to realize slightly complicated scenarios, like preparing breakfast, cleaning, doing the dishes, and so on. And they are skipping this grounding problem as well. So there is a huge gap between signals and symbolic domains. So what I was proposing here is, with my PhD work, is if we use somehow the invariant object relations, we can actually convert this continuous sensory data into quite descriptive but discrete information, like key events that can act like a symbolic information for the robot. Okay? So we are not using any kind of assumption about or prior knowledge about the objects or actions. We have no idea about the objects in this scene. We just take a look at their symbolic interactions. From that, we derive grounded symbolic information. Okay. With that, I mean, semantic here basically refers to the meaning of the action, and consequently, semantic event chain, which is the name of this framework, it grounds high-level discrete action primitives, like those symbolic information, into the low-level continuous sensory data. Okay? That is the unique thing that comes with this event chain concept. So how do we do that? Assume those are the videos, but for the sake of simplicity, I just show the snapshots. Assume like here, we are showing how to cut a banana, how to do stirring, how to hide an object, and so on and so on. What we do is we use nowadays you can use foundation vision models, or you can use classical image processing techniques to just segment those entities out. Okay? Segmentation is nothing else than dividing images into regions. So here, every color represents one entity in the scene. It could correspond to one single object, or it might also represent a part of an object. We don't know. Okay? And the unique thing is that those, or the only assumption that we rely on is that those segments should be trackable. So during the course of the action, the color of this hand, for instance, should not change. There must be no flickering. Okay, that's the only assumption. So that means we should have a segmentation and tracking. Okay? So what we do, we take those segments and represent them by graphs. Okay? And we draw a graph node at the center of each segment, and then draw a notch if there is any interaction. Let's say if they are touching each other, if it is on top of another object, or if it is inside another object. Okay, it depends on your perception algorithm, how good it is. If you can handle all these relations, spatial relations, you can attach them to those edges. Then it becomes a weighted graph. Okay, so at the end of the day, instead of using, let's say, 100 images in your manipulation, just use 100 graphs. Okay, and what we do, we just convert them into graph sequences. Okay? And then we analyze those graph sequences and find their the changes in these graph sequences and represent those changes by matrices. Okay? Now, from now on, those 100 RGB images are converted into, let's say, 5x5 or 7x7 matrices, and we call those semantic event chains. So event chain is just a matrix. Okay? At the end of the day, encoding scheme of a large manipulation action. It is beautiful because if you take a look at the relations between those matrices, then you can basically classify. And when you roll back to the original images, you may see, okay, those are the actions that are pretty much giving the same message. So type similar actions where you are doing cutting, where you are also showing how to stirring, and so on and so on. Action classification is one thing that you can do by using only those matrices. You can go one step further and investigate which tools perform the same role in the very same action. And here you can say those are the tools that you use for cutting. If you were using spatula for cutting, which is totally fine, you can do that. It will also emerge here. Or you can use the same spatula also for stirring, like a spoon. Okay. And again, here we have no idea about object type itself. So the robot is not using any kind of object detection algorithm. Okay, we'll come to that one. And so given enough training data, you can actually learn the similarities between those matrices because you know which of those are falling into the same group. You can do classification. Once you do that, you can basically learn the similar rows and columns, and you can keep them in the memory so that you can replay the actions with the robot. Okay, so you are basically here the ultimate message is like by using this event chain concept, we are trying to have like a holistic concept, holistic semantic concept of the actions, so that they are generic enough to be used to learn the action consequences, like what kind of action. Is it something that is destructive? It is something that is basically changing the orientation of the scene. And you can use it to distinguish between different manipulations. You can use it to categorize manipulated objects. Again, you are not recognizing, but categorizing the objects based on their roles. And you can go one step further and execute those actions by replaying those matrices. I will see that very soon. And there's also potential to link this thing with language because this is symbolic information. So does the language. So there is a way to link the word. Like if you give a textual description, like a person is cutting a cucumber, you can link this term cucumber with the segment that is visible in your RGB image. So this way the robot can say, okay, this pixel in my image is the thing that you are referring to be cut, and so on and so on. Okay? We have a publication on that one. And you can also use the very same concept to memorize. So in a more memory-friendly way. So you don't have to store all the information in memory, because when you see a new instance of an action, you may see the differences. You may say, okay, let's say all the objects are the same, but the trajectory is slightly different. Then maybe I should update my trajectory information instead of updating all entire thing for the action. Okay, so those are the things that we can achieve by using the very same concept. And we have publications at top journals, I will say. So how does that work? I will spend the next 10 minutes to give you a bit more insight about this event chain concept. And then we'll talk about the applications. So assume you are showing one action where the human is showing how to cut a cucumber. Okay, instead of having 100 frames, I just show you some snapshots because what we do is we take those, we segment them out, we track them, and then we represent them by graphs. Here, let's say graph number 9 is representing the right hand. And what is that? The knife is number 6, cucumber is number 2, and so on. And since hand is touching the knife, you have an edge here. And after a while, the edge is disappearing because you're leaving the knife. Okay? So what we do is we write down pairwise object relations. So the relation between 9 and 6, relation between 4 and 2, relation between 1 and 9, and so on and so on. All the relations between every object pair. But some of the objects are not playing any role because they are standing in the back and you may accidentally touch them. So that is why you at the end of the day, you will get rid of those noisy ones and you will have only those, let's say, 3 pairs. And the relations between those, let's say 9 and 6, are in the 2D domain, oversimplified 2D domain, are nothing else than having overlapping, not touching, and absence. You cannot have more than that. Okay? So the hand can maybe touch or not touch and so on. But in the 3D space, it will be more complicated. Of course, you may have inside, above, or half inside. You know, you have to discover all those relations. But let's stay in the simplified 2D domain. So you write them down for every single frame. Like, what's the relation between those two? Is it absent, absent? Then it becomes set, not touching, and then touching, and so on. Then you just do subgraph analysis. So you just compare the eigenvalues and find out the changes between the graphs. Okay. You say that there is one graph which is happening all the time, and after frame number 100, it switches to another graph. Okay. Then those are represented here as a column. So each column represents one main graph, which can be autonomously extracted by using this single value decomposition algorithm. Okay, nothing special here. For the sake of simplicity, I just show that this is the column representing the instance where hand is still not touching the knife, or maybe it is just touching the knife. And then we have an instance where the knife is approaching to the cucumber. And then the instance, this is the one that where you are doing actual cutting and so on and so on. Okay. So every column represents one primitive for us, time descriptive information. It actually tells you when to pay attention to the action. Is it now where we should pay attention? Maybe, yeah, but is it now? Is this the time instant that is super important for grasp, or is it this instance? It tells you that whenever you touch the object, you should pay attention. Whenever you lift the object, because the connection between the table and the object is disappearing, so it is the instance that you should pay attention. Okay, and the roles are just the spatial relations. Okay, that's all. So what we do is, okay, so here just a side note that this is fully interpretable by design, okay, compared to these black box data-driven encoding algorithms where you put all millions of data, shake it, and hopefully you get the latent representations, which can be used for. It works, that's totally fine, but the grounding is an issue. Okay, here it is fully observable and interpretable. Then what we do, we take all those columns as one state. Okay, primitives are considered as state. Now it becomes a state sequence, right? And we just assign weight values for each row and then assign weights also between the transitions between the columns. Okay, let's start with 1. And whenever you have a new sample, because you can compare the weight chains and then you can find the similarities and then you can also update the weight values if those states are also existing on those similar actions. Okay. Here, the red sequence is representing those states that the humans have already shown most frequently. Okay, so that means most of the people are following this steps. Some people also follow that one and that one, but they are a bit noisy because you have less space there. Okay. This is for cutting and chopping, and you can also do the same thing for stirring, and you will get a totally different state sequence representation. Okay, so that means the event chain concept is good at capturing the state sequence from human demonstration. It's just like basically following the Markovian assumption compared to, for instance, hidden Markov models. Here, states are fully observable. So you do not have to say there must be 5, there must be 10 states. No, it is discovered from the data directly. Okay? That's also another beauty. So what you can do is you can take those states and then take a look at, roll back to your training data and say, okay, since I know which objects are having the same role, because you can compare the roles. From that, you can find out number 9 in this sample corresponds to number 10 in another sequence. So you can just take a look at which segments they correspond to. So now this is number 9 here, for instance, one action. Another action use this thing as a tool and so on. So you can basically categorize objects based on their roles in the action. So we call them primer objects. We still don't know what they are. We call them primer objects. Those are the secondary objects that are used to be cut or chopped in this action. Okay, so those are very abstract representations for objects, and this is the abstract representation for the action itself. This is very interesting because the columns are playing super important role when you want to do execution. They tell you again when to pay attention to the action, and that means, let's say, until here you are doing the approaching, and between those two columns you are actually doing the cutting, actual cutting. And then you start talking about withdrawing and so on. So that, what does that mean? If you go back to the training data, you can extract the entire trajectory information. Now, instead of keeping all this history, you can basically get the chunk of the trajectory, and you can say, okay, this is the time instant or time interval where the actual cutting is happening. Please store this information, not something else, because today you may follow this trajectory here because maybe this scene does not have any obstacle, so you can directly approach. Maybe tomorrow there will be an obstacle, so you may follow another trajectory. But this is not that much relevant for actual cutting. Okay, so that is the beauty of this. And another interesting outcome from this algorithm is that it basically takes a look at the consequences of the actions. That means the cutting and chopping, they are falling into the same group. If you semantically think about that, at the end of the day, what you do is you divide objects into 2 parts by either following this trajectory or by following that trajectory, right? For the chopping, you have to apply very fast motion, but it is destructive, right? At the end of the day, you get a new object out of that. So here you can again see that inside this same interval between those two primitives, in one action you can see this, in another action you can see this chopping-like trajectory. And you can store this information again instead of the entire trajectory. And this is super important if you want to form a declarative memory concept, like a long-term memory, where you talk about the changes in your demonstrations, okay, in a more memory efficient way again. It actually falls into the same concept that Piaget was proposing already in the 80s, saying that once we observe a new instance, totally new, that a new concept that we have not seen before, let's say you have not seen a dog before in your life, what you do is you create a new chunk in your memory. You associate this concept there. You create a new memory segment and you put this concept there. But if you see another instance of the dog, you do not create a new segment, but you update your already existing segment, memory segment, with this new information. It's exactly what we are trying to do. Do not create a new segment in your memory. Just update your already existing segment with this slightly different trajectory part. Okay? Then what you can do, you can send this trajectory directly to robot to execute those actions for you. So here we just show how to do the cutting action. So the robot is now executing only this trajectory information by using the concept of DMP. Okay. You can do more than that. You can ask the robot to first approach the knife, grasp it, then grasp the knife, and then approach to the cucumber, cut it, and then withdraw, like the way that you showed, like the whole demonstration. Okay. And when you talk about robot executions, then things are becoming a bit more complicated because then we have to talk about also onboard sensors and the detection of those primitives and spatial relations. They are becoming a bit more different. Here, for instance, we're using the haptic information, we're using the trajectory information of the robot, we're using the force information, just to find out the time instances that those changes are happening. Okay, so when you go from here to here, the sensors are telling you that, okay, it is enough to finish the cutting because the knife is touching to the table and you get high force feedback. Okay, and then what you can do, you can put those primitives together, like cutting, approaching, and then pouring, storing together. Like you can chain them because you can learn one chunk for each, and you can execute a slightly long and complicated scenarios with that. So here we show how the robot is preparing a kind of breakfast or salad. He was cutting a cucumber first and then pouring into the bowl, and then there was another ingredient, and then grabs the knife, spoon, and then stir it. Okay. Good. So this is like the summary of the framework, and it is basically the slides that I have shown up to now was basically about 2D. Now I will just show you how things were done in 3D. This is the work that I have done at KIT. There we had a motion capture system. The objects were also having those small, tiny entities to get the perfect pose. You can get the point cloud, you can get the graphs, 3D graphs out of that, from which you can also get the spatial relations very easily because you know the models of the object. So unless knowing the model of the object, you can never and never say that the object is inside another object. For 2D vision, it is next to impossible from our experience. So we were using the modeling here. And you do the very same thing. In this case, the relations will be slightly different, but the same matrix will be there. And you use the similarity to classify actions and categorize objects. From that, you can generate the states. This is the thing that I was talking about, and then learning, and then you can form a new memory segment so that the robot can do the execution. So you start with the perception and put the execution framework there. And right in the beginning of my talk, I was talking about the signal to symbol gap. So here you are at the very signal level, the pixels are there. There's a huge variation. You have no idea how to draw the abstract representation. But now with the symbolic representation, you achieve high degree of invariance. So no matter what kind of colors or object types you use, you can really get the very descriptive abstract representation. Since you're in the symbolic level, you can link this thing with language. I will skip this part. I have a backup slide in case you're interested in that one. We also show how you link those rows or columns together with the textual information that you provide. When you say there is a knife, you can link it to number 9 here, for instance. And you can also attach sub-symbolic information. Let's say in one of our work, we just show how we can generate latent representation of those videos, RGB image sequences, and these latent vectors can be stored as an episodic memory. And you can use this thing to even regenerate the action. So when you put a cup in front of the table, it might be totally new cup that has not been used in the training data. Robot can replay the previously observed episodes, basically those latent representations, and regenerate the expected scene, basically RGB images. It can say, okay, now I'm expecting that image, the cup should be somewhere here after pushing. So there is a way to enrich those abstract information with subsymbolic representations. So there was another RAL paper that we showed. Great. So this is basically the holistic semantic representation that I was trying to explain up to now. Okay, and it has been used in different European projects. Just to give you the capacity of this framework. So in one of the projects, we used the same event chain concept to solve puzzle. Assembly task by Robot, the same UR3. No, it was UR5 at the time. It was from Nobel's group. And the robot was using the graphs and this event chain to go from one to set another one to solve the assembly task. We used the same graph technology the graph idea to track leads. So the robot gardener can say, okay, now the graph nodes are not becoming greenish, so that I should apply more water or I should change the illumination. And we also did a very interesting experiment with human subjects. We were working together with psychologists, and we showed the very same video to human subjects, and we asked them to decompose those actions into chunks, like we did with event chains, and we compared our results. And here it shows that the black dots, event chain results, are matching very well with the way that human is decomposing the action. So when we show this action, human also says that, okay, this is the instant where the actual change is happening. So our engineering solution is basically matching very well with the way that humans do reasoning. And in another work at KIT, we also showed how to use the same decomposition algorithm to replay the actions at different temporal scales. I was coining the term temporal scaling. So when you show how to do wiping, let's say in 2 seconds, the robot can autonomously repeat the action for you for 2 minutes, or even for 1 second. So he can do scaling himself autonomously. And along the same lines, now I'm collaborating with one group in Barcelona. We do this very same reasoning with deformable objects. So is it any possible to apply semantics for plots? Can we extract the semantics, compare them so that the robots can learn from humans and repeat them? So we were showing the human was showing how to fold one cloth, and then we were transferring this to different robot manipulators. And we have 2 different robot manipulators here that can imitate the humans. So just to give you the idea of the scalability. And I'm also collaborating with Sanam Sarial from ITU. So we had 2 PhD students. One of them is working on the perception of failure detection. So when the robot is doing something, maybe failures may happen. So can we detect this thing by fusing the sensory information, audio, RGB depth, and so on? Is it also possible to anticipate this thing in advance? If so, can we also learn how to prevent those by using reinforcement learning concept? Another student was working on that one, and we had 2 RAL papers which will be presented at ICRA next week. Up to now, I was talking about the work that is basically in this group. Now I will spend the next 10 minutes maybe. Let's see how are we doing good with timing? Okay, we can continue. With the semantics-aware learning in autonomous vehicles. Since last 5 years, I have been working on this subject as well. Because when I moved to Sweden, I got the chance to work together with the AI team at Volvo. There we were developing an autonomous truck. We had a very large sensor setup, a very good perception team. There we implemented this very interesting work, which is called Salsa Next, which was basically taking the LiDAR. The LiDAR is a sensor that gives you the 360-degree scan of the environment. So you get the full point cloud of the environment. Like the Kinect device, you get on the front view, but with that guy, you get higher resolution, but for the whole scene. Okay? this version of the LiDAR, to be honest, was even more expensive than the car itself. So this is just a side note. This is not something like a small toy that you can play around here. But there are cheaper versions, don't worry. So what we did is we implement a network that can take this full point cloud and segments this into regions, semantically meaningful regions. Like this purplish area is your drivable area, and these blue points are representing the vehicles, buildings, and so on and so on. For the sake of simplicity, I just project them into the RGB space to show you how it looks like, because for unexperienced people, this has no meaning. Again, this is only LiDAR only. So this framework is using just LiDAR sensor. There's no camera at all. But here, for the sake of simplicity, I just show them here together. Okay. But this network was unique at the time because it was not only giving the semantic classes, but also the uncertainty. So it's super important for autonomous vehicles in safety critical applications. When you say there's a free space, you should trust this, otherwise the consequences could be might be harmful, right? So it was giving you the epistemic uncertainty, which is highly relevant to the amount of the data, or aleatoric uncertainty, which is coming the uncertainty coming from the sensor itself. Okay? So the network can return those two as well as like a lightish areas here. Okay. And it got quite some citations, became like one of the fundamental or base models in the upcoming AI model. So it was good for the community. And it's super important because now it gives you, because we know that neural networks are over-parameterized, so they're not that good at being transparent. So interpretability makes clear what the system knows, while this uncertainty-like approaches reveals what the system does not know. So the system can also be aware of the fact that there might be things that he is not sure about. Okay? This is super important safety critical applications. So what we did is we took this base model. It was a collaboration with Volvo. Then we continued the collaboration. So you take the LiDAR, the projection, and then you apply this Salsa that I was talking about in the previous slide. You get the semantic segments. Okay. You can do the very same thing with camera images. You can take the camera. You can use any state-of-the-art algorithm and you segment it out. Okay, you have segments in the RGB space, segments in the point cloud space, but this is a projection. You can use raw point cloud-based approaches. That's totally fine. What we did is we gave this thing into a conditional network, a generative model, C1. So you give the segments of the LiDAR together with the original X, Y, Z and the intensity values. The network was trying to convert this thing into a fake RGB segment. They convert the LiDAR segment into RGB segment. Then take those, send it to the discriminator so it can, really boost the performance for you. Okay. Once you trained, you take the fake RGB segments, send to another state-of-the-art network. This is from NVIDIA, so that you can convert this thing into RGB image, fake image. So this is image-to-image translation, nothing special. This is image-to-image translation, nothing special. But this is cross-model translation. You go from 3D point cloud into 2D image. And each sensor has fundamentally different working principles. Okay? And then, okay, you have this, then the original image, and there's a discriminator, so it learns how to generate fake RGB image. Story is the following. You take the full point cloud like that. You segment this like here. You generate camera is segmented version of the camera space like here, and you convert this thing into a panoramic image, RGB image. It's quite interesting because don't forget that in this setup, the vehicle has only one single camera that sees only this area. So there is no panoramic camera that sees the area surrounding. By using this framework, the vehicle or the robot can use other modalities to generate beliefs about the surrounding. So this is a panoramic fake image, and this is the actual RGB image that it sees from the environment. Okay, and this got basically the best student paper about at Ichikai workshop, organized by CMU people. And when you run this for an entire sequence, we are not using any temporal information here, by the way. Okay, it's only frame-wise. This is why you may have this flickering effect, but it's very beautiful. It was the first attempt in the field, because now, assume that you have the autonomous vehicle, you go on the highway at 30, 50, 90, that doesn't matter. All of a sudden, your camera stops working. what to do? Sensor failure. Of course, you can have emergency brake, but we are talking about intelligent vehicles. Having emergency brake is not an indication of having intelligence at that level. What we humans are doing normally, if I say you close your eyes and do reasoning, I'm pretty sure you will say, okay, there's still free place, I can still move around. Of course, not for the next 5 minutes, but at least for upcoming 5-10 seconds, we can do the freezing. This is what we are after here. Can we use other modalities like haptic, like other LiDAR sensor, to create our beliefs about this? And this is exactly what we generate here. RGB fake images are our beliefs. What we did is we went one step further and we update our framework by just predicting the depth information as well. So you can have another network which takes the RGB, generates fake depth, send it to your slightly more complicated GAN model, so that it can generate not only fake segments, but also fake depth. This is basically multitask learning. And we showed that if you do that, since those tasks are complementary and fundamentally similar, learning one task is actually helping the learning of other tasks. So if you run this network for individual tasks, you get lower performance. This was quite interesting outcome, I would say. So if you design this thing in a smart way, then this multitask learning can boost the performance for every single for individual task as well. So now what you can do is you can generate the fake segments, fake depth, and fake camera image. This is now the most advanced version, which got published this late last year. Okay, you may say, so what? I mean, no one will deploy this thing to vehicle today, and it might become a bit challenging. And scientifically, it might be interesting, but for convincing the companies, it might be a bit of questioning, you know. So what we did is we showed another interesting application. It is because we know the drawbacks of those individual sensors. So this is a sample scene from a kitty data set. If you have a black light objects, your point cloud coming from your LiDAR will be even sparser. Okay, like take a look at here. It is a problem in the LiDAR space. People work with LiDAR, they're aware of that fact. So what we say is that if you use this fake depth, you can generate fake point cloud. We call it pseudo point cloud. And here you can see that dark grayish point clouds are the ones that are generated, and the red ones are the original LiDAR point cloud. Okay? Now we can use this thing for object detection. Okay? Take SalsaNext, go to the TitanNet, the same framework, nothing special, generate the point cloud, attach it to the original point cloud, and then run your any kind of object detection. Okay? At the end of the day, you will get the semantic segments plus bounding boxes with denser point clouds. Okay? So those grayish area is showing how dense the point cloud becomes by using this framework. So in theory, if it is the case, then it should boost the performance for object detection, and this is what happens. So if you use any kind of state-of-the-art object detection methods without changing anything, take it and apply it to our dense point cloud, you see that the performance goes up for any kind of. If you go with spatial networks that are particularly designed for pseudo point clouds, you get even higher performance, like about 3% improvement. Okay, and this is the result that you get after that, and just got accepted, which will be presented next month. All right. Just to summarize all these things that I talk about, it's actually part of a very big European project that I'm honored to coordinate. So Fortas is also part of that. We are collaborating. So we have I would say like 4 or 5 different vehicles with full sensor stack, and we are really going to the North Arctic Circle. We do experiments in Turkey, in Istanbul, Eskişehir, and so on, Ankara. We also go to Germany. We also go to right to the up. Finland, Lapland region, which is the test area where real vehicles go there to test their normal vehicle performances. And we will go there to demonstrate how our perception and control stacks will work under heavy snow. So this project is just about autonomous driving under really bad conditions, weather conditions, harsh weather conditions, like heavy snow, heavy rain, heavy fog, and so on and so on. And there's a very large consortium behind that. So just to show you a bit of results on that, we in Halmstad, in my group, we have implemented the fastest algorithm in the world that can take real LiDAR point cloud, corrupted under snow. So these black points are representing your snows. While you are having snowflakes, you will get this corrupted one, and we show that your object detection performance will definitely go down. You have to do training from scratch with new labeling and so on. instead of doing that, we said maybe we can use AI to get rid of those snowy point clouds and filter them out. So we have just implemented and released the code which can basically do this thing in real time and gives you pretty much the same performance compared to state-of-the-art algorithms. If the slides comes. Okay. Let's go step by step. We have also one facility in Germany where we generate a new data set, and there it's a kind of controlled environment. We call it rain tunnel. You have sprinklers here, which is giving you artificial rain. From that, you can get the LiDAR data, and we've introduced a automatic labeling tool, which can basically distinguish points that belong to the raindrops. It is super important because you can have a mathematical modeling. You can use it for training your network, you know. And it is the first in the world, by the way, this data set, and we'll be releasing this thing in the upcoming months. And we have also implemented another framework where we collect data on the really snowy cases. This is the data coming from Finland. And we have the full scan point cloud of the environment, and we have labeled that. So this is also going to be the first labeled point cloud under snowy conditions, which can be used to train our models and so on. Just initial, a short snapshot about the initial results from the project. And I'm actually looking for students that can work with us for short term, like 3 to 6 months. If anyone volunteered or willing to come and work in this very lovely summer destination in Sweden. Darza was there for last month or last week. You can already study how beautiful it is, just to motivate you a bit, in case anyone is interested. With that, I'm done. If you have any questions or comments, please.